I'm going to run a circle, simulation of a circle, with the name, chromatic numbers, and more. And maybe you read an extract that I invented, the story, just to make it a little more interesting. But if you haven't, that's okay. There is no mathematics there. Before I start, I have to tell you a little bit about this particular session of math circle. I actually ran it a couple of times by now. One time I did it in my own circle, and I told you that we have 2 hours, so I ran it for 2 hours with kids that I know, and I knew the level of the kids. I knew where to start and how far I can go and how much we can cover. Of course, I didn't cover the whole thing, and you will see the handout, and you'll see what's in that handout. Even with the kids that I knew, and with the time I knew, and with everything known to me, I still wasn't able to cover the whole material. And this is what always happens to all the leaders that I know of. We always prepare too much material, and one thing that we learn over time is that we should not try to cover all that material, even if we feel that we have so much stuff and so much interesting stuff, and that we would love to really do all that. That's a big mistake. We should really go with the audience, and to cover less is better than to cover more. That's it. Well, I see some people agree with me, and that's really nice. Well, the next time I ran the same session was at Stanford Math Circle. We have in Bay Area, we have now lots of circles, and the Stanford Math Circle was founded by Sam Vanderbilt, but then Sam left us, and now different other people are running it. Currently, the director of that circle is Dana Paquin, and she's doing a fantastic job. And when she started, when Sam started his circle, he expressly wanted it to be for high school kids. And I thought it was absolutely wonderful for us, because we now had a place where our students could graduate to. Our circle is for middle school kids, and when they spend a few years with us, and then they outgrow us, and there was no place for them to go before that the Stanford Circle started. But then, when it started, it was wonderful, because it's very near, geographically it's close, kids had no trouble getting there, and so that was nice. Well, as with all circles, that circle became younger and younger and younger. And even though when Dana became the director, she expressly told me that she wanted to make it for high school kids. No way, it became middle school kids mostly. And so I sort of knew, I anticipated that it would be mostly middle school. Well, I come to give this talk, and I see kids sitting in front, and this is a big auditorium, tiered auditorium, and I sit in front, I see a bunch of kids whose feet are dangling. They're young kids. And those young kids became the most active participants. Every time I would ask a question, all these kids would run to the board. It was not enough for them to just scream and yell and tell the answers. They would run to the board, and, like ants running around and putting stuff on the board. So that was a little bit difficult. And I definitely had to change change my talk while on the go. But still, people mostly had fun with that. Now, what I'm trying, and again, I had almost 2 hours there. They have 1 hour and 45 minutes. Well, here I'm going to do it in 1 hour, and I already spent some time just talking about it without doing it, so I'm having a list time. So let's see how that goes. And I'm planning to run a similar thing in our teacher's circle, which will be a month from now. And that will be a totally different animal again. And with teacher circles, it's much more difficult thing to run it for teachers. Teachers, kids have no difficulty, whether they understand something or don't understand something, they are not inhibited. They just love it. They enjoy it. Teachers are different. Teachers feel that they have to know the stuff. Teachers feel that they are professionals. They cannot admit that they cannot solve something, they cannot do something. It takes a lot of effort to convince them that no, it's fine. It's fine not to be able to do things. But it's still, it is, I don't know how it's going to work with teachers. So, Sam.
I found my backpack,
Oh.
but I did not find any piece of paper that said anything about chromatic numbers across it.
Is it possible to run some copies? I have my
If you have a copy, yes, I can do
yeah.
that.
So if I find it in my suitcase. Well, I apologize. That is kind of miscommunication. I was actually sure that it was
If you talk a little bit about how to run a master I'm Sylvia Chang, I run the Colorado Math School, and I find that if you let the young kids in, the older kids stop coming. So I actually let very, very few of the younger kids in unless I'm sure that they are mature in behavior and that they fit in well with the high school group. Now, maybe in some areas that's very difficult. Maybe the strong kids are all younger kids, and so you can't really keep them out. But for social reasons, I try to keep the middle schoolers in the middle school group, and some of them are very strong, and not bring them into the high school group because in the high school it's just tough. So just a brief comment while you were getting your
yeah. Okay, so let's start without the handout. Well, suppose that, just imagine that you are on a vacation island, you have absolutely nothing to do, you have no worries, no duties, no nothing. You have lots of time at your disposal, and you have an infinite supply of colored paints, different colors, and you have lots of blank paper, and you let your imagination run completely wild. What can you paint? Are there any restrictions on what you can paint and how you can paint? Why shouldn't there be any restriction? You have lots of paper, you have lots of colors, you have lots of time. No limits, right? There is no limits. Okay. For example, how about you have this weird idea? Or I have this weird idea. Would you help me? I have a plane, so this is an infinite plane. I want to paint every point of that plane, every point of that plane. And I just put these conditions on myself, these restrictions. I want to use exactly 3 colors. Well, to make my life even easier, one color is going to be white. So I have white, blue, and green. I have exactly 3 colors. So I want to paint every point on this plane using one of these 3 colors, but I want to do it in such a way that on every line of this plane, we have exactly 2 colors. So every line on the plane must contain points of exactly 2 colors. But altogether, I have to have points of 3 colors on the plane. Is it possible to do that? Well, think about it. Talk about it, think about it, draw something.
If this is a point, or a square.
No,
Point's not a
you have
square.
to use 3 colors. Altogether, on
Yeah.
the plane, you have to have how
If it were a square, we could do.
blue, green, and white. Yes.
Yeah, okay.
I'm sorry. Okay, if we did So if they were squares along one line, we could do like 1, 2, 1, 2, 1, 2. And then the line above would be like 1, 3, 1, 3, 1, 3. And it would just be like.
What about the lines and slopes not, the lines and slopes?
Oh, I was thinking horizontal lines.
I know. I thought the same thing. I thought, you know, each line gave two colors, and then staggered the place where the colors change. But then no matter how you stack it,
The third color.
Yes, you have to use all
and
things.
what's the color that like? In other words,
Every line emanates. Oh, yeah.
touches that.
Oh, because if, right, you could do it in just black and white, like checkerboard, and it, but or diagonal, so mess it up. I mean, I get that a point's infinitesimal, so I don't understand why.
Yeah, right. I don't understand. Good way to phrase it. I understand.
So if you've got the one,
I mean,
then you put the one down.
All right.
Then you have
okay.
to sort of do concentric
If you have a triangle,
then the line each
point is on two lines, right?
an actual line.
If you have a triangle with three different colors,
Well, no, that doesn't
then
work.
automatically each side contains two different colors.
No. Yeah, no.
This line got you all the way through it.
If you have three different colors, you have one triangle.
Maybe different color, well, maybe,
There exists such a triangle because you have three different colors.
worried about the
Well, next question. How many pictures?
But I don't.
Yeah, exactly. That's right. So, really,
Now, I'm going to reveal the solution for you. The solution is very simple. They don't like blue color, I guess. So they made exactly one point blue.
For 2.
And then they draw 2 green lines that intersect at that point.
We just thought you could put any number of lines you want.
Sure, yes. Or any number of lines.
Finite number.
Okay, so that's it.
Yeah.
That's the solution, right? Have any line on this plane, if it goes through the blue point, it will have white and blue, unless it is one of these 2 lines. If it doesn't go through this point, it has green and white. So every line on the plane has exactly two colors, but we have used 3 colors. So of course there are lots of other questions that you can ask. How many different solutions, essentially different solutions, can we think about? That's one possibility. Another question to ask is it possible to have an additional condition that every color has to be used on at least 2 points? So here we use one color is used on 1 point. Is it possible to invent a solution where we use every color at least on 2 points? And you can invent any other questions like that. So at any rate, what that shows looks like there is no really restrictions. That was a kind of weird restriction, and you solved it in almost no time, right? So it looks like we're so free to do whatever we want. Yeah.
We can do it with 2 points if we're on the sphere. And we
Play. Oh, we're talking about play. But again, this is another. Good problems are like mushrooms. Once you found one, there is always lots of nice problems around. Okay, but now let me ask you another question. Are we and this is to show you that maybe we are not as free as it all looks. I claim that if I use exactly 2 colors, green and blue, and I'm not as ambitious as painting the entire plane, just one circle. I have one circle in the plane, and just imagine I have one circle, but I don't draw it because I want to paint it. I want to paint all points on that one circle, either green or blue. Is it possible to do it in such a way that no isosceles triangle is monochromatic?
You're coloring
No
in the
isosceles
circle?
No, you paint one, just a circle. You have a circle.
Just the vertices.
Just a circle. We don't well, not inside, not outside, just a circle. And you use two colors, blue and green. Can you invent a scheme where no isosceles triangle will have all 3 points, all 3 vertices of the same color? Is the question clear? Okay, good. Think about it.
3 vertices.
So you've got to
You don't want to avoid that.
You're going to draw all
So if you have
possible
one blue
equilateral
point,
triangles that I mean,
that's the
Isosceles.
isosceles concept. Diameter.
all possible ones in such a way that every possible one is 3 colors.
Has to be here, and there has to be at least 1, 3.
We use 2 colors to paint certain colors.
Right, so suppose, just to start, you have one side
But then it's really easy to make a sausage triangle that has some on the side.
Very much.
yeah, okay.
So there's 2 colors. 2 colors.
Suppose you made
Well,
it.
okay, let's put it this way. What about the point diametrically opposite triangle? Here you have to be the point.
Well, that is
No.
So now even if
There is a question, I'm talking about triangles with vertices on the surface, of course.
So this is
You have points on the, you choose any 3 points on the circle that define the triangle. Is it possible to create in such a way that none of the isosceles triangles can be constructed that way?
so I've got
Have the same colors.
maybe this and then the bottom one has to be
Well, that is sort of, okay, what I was trying to say is,
Yeah, I'm listening.
if you look at like
these are both.
if it's green, it's not going to these two.
you sort of,
And then they actually
It can't be solid blue, but it has some bizarrely chaotic mixture of blue and
then
blue.
that's
I was thinking about this shape because maybe this shape. Done. QED.
At any point, you need your head.
Pick any 3 vertices. What shape is your triangle? Okay. There have to be 3 vertices that are the same color because there's 5 vertices.
yeah.
2 colors. There's 5 vertices.
Yeah,
So some 3 of them have to all be the same color.
So,
And any 3 vertices in the regular pentagon make an isosceles. The pentagon inscribed in the system.
Oh, and there has to be a pentagon in it. Okay, got it.
so he says that it can't happen.
I was trying with the hexagon, I couldn't quite get it. Because with the hexagon, there's these triangles that are isosceles. With the square 4 points above them. So 5 would tell it. So you still get isosceles like you do with the squares. Okay, so then think about the 3rd vertex. Once you choose 3 vertices, depending on the 3rd one that's also adjacent, still isosceles. Another one
All right. We have one book solved.
and these are not symmetrical.
Now I know. I got it.
Nice diagram. when you think about the most important diagram in the world, of course, it's a pentagon with the pentagram inside. And what is, it's a regular pentagon. And every triangle is isosceles here. That's easy to see. Every triangle with the vertices is isosceles. Now, you have these 5 points. If you color them using 2 colors, it is inevitable to have three points of the same color.
Right.
Done.
Done. Nice.
Everybody got it? So it is impossible. You know, that simple restriction was not possible to overcome. So we're not as free as it looks. There are some things that we can't do. Now again, an interesting question would be to ask, what about equilateral triangles? Is it possible to avoid monochromatic equilateral triangles? I have no idea whether it's possible or not. I have no idea how hard that question is. But it is always a nice thing to have questions like that, which might happen to be very hard. But at the same time, if they happen to be easy, nice. Your kids are happy because they solved it. If the question is very hard, so much the better. If it sparks their imagination, they might spend lots of time trying to struggle with it, and maybe along the way they will find something interesting. Yeah?
Did you mean 3 colors or equilateral?
2 colors.
Because
2 colors.
it's easy to avoid, I'm sorry, it's red. It's easy to avoid.
Equilateral triangles with 2 colors? See, it wasn't an easy problem, but how happy that student is. Okay, so now we have, these were sort of warm-up questions. That shows that on the one hand we have lots of freedom, but on the other hand we are not completely free. So, one very simple question. Well, the plane is too big. Circle is probably kind of too circular. How about just one line? We have one line, just one line, and we want to paint it, every point on that line, using exactly 2 colors. And we want to do it in such a way that no 2 points exactly 1 unit apart are of the same color. Is that clear? All points on the line are painted using exactly 2 colors, so each point is either green or blue. And if you have any 2 points exactly 1 unit apart, they cannot be of the same color. Can we invent coloring of this type?
All rationals belong here.
There exist 2 rationals in 1 unit. The solution is just
That's what it seems.
Yes, that works.
0, not quite 1.
Yeah.
Make sure it's not
But you're right, you can make any pattern.
So
There was another thing.
Another geometric part.
think of the interval.
Yeah, I knew that. You know, the circle with I think that's
This point here is
That's exactly what I was thinking.
every other point is can they say
where you start.
If you look at the integers, they have to alternate colors.
Yes, right. That's what I
And
was.
then any point in the interval 0, 1, you can color whatever color you want as long as the thing, the unit distance from that alternates. So you can color the interval from 0 to 1 however you want. And then cross 0, closed, infinity 0, non-infinity purple. And then copy that alternate.
You can't color it any way you want.
Color the interval from 0 to non-including 1 any way you want. And then just copy it,
Oh,
alternate.
copy. Yeah, I was like, you have to, right.
You alternate.
Right.
Copy it.
Oh, and you're just choosing to drag it. I mean, you're choosing to copy it for 1 unit.
Copy it 1 unit over and
1 unit minus the point.
What is the same about these solutions? In each case, you're starting with kids and
Okay, so what's solution?
well, here each point is part of family. It has to alternate colors from each part.
yeah, that's not.
I'm sure that
No, they bring that.
All right, his
Yes.
So, you see what I'm saying? With the one point,
The problem with there is not finding that
I am cutting it over it short because I am not doing what I told you needs to be done. I told you that it is not important to cover the whole thing. It's important to just let people enjoy the stuff. But I always break my own rules, of course. So I'm breaking this rule. And well, besides, some people solve it. And one of the solutions that it took me a long time to actually understand what some of my kids were telling me. They were telling me, well, paint every other one blue and every other one green. Now, in fact, I heard that in both cases, in my own circle where I have middle school kids who are pretty sophisticated, and also in the Stanford circle where I had all these very, very young kids. But they meant different things. Kids in my middle school circle actually meant by every other one. They meant all the integers on the number line. Just start with integer points. This is 0. This is 1. This is 2. This is 3, and so forth. This is what they meant. Of course, then after that, we have to talk about the fact that there are other numbers besides integers in the wall, and they agreed eventually. But that was a very nice beginning of the solution, really. But kids and the little kids literally meant every other point. Oh, what do you mean? Oh, this point is blue, and the next one is green.
But that solves another problem. Can you color a line with the two adjacent points that are always different colors?
Yeah, that would be interesting. Okay, anyway, I think that everybody sees the solution now, right? So every integer point is painted, and then let me paint all of these green, and let me paint all of these blue. And let me paint all of these green again. So we have half open intervals. Yeah.
So we were talking about what these three problems have in common and how you can motivate these. Is there a common motivation, the solution? And what we sort of came up with was the idea that there's a key subset that you're looking at. In this case, it's the integers.
Yeah.
In the circle case, it's well, the way we did it, it was various inscribed regular polygons. In the case of the three colors, it was a point and then lines through the point. And that's the kind of thing that I find that high school kids will get into. Middle and elementary school kids, they're too busy solving the problem and loving that they solved it. But high school kids will talk about that.
Great. Well, I'll try to do that with teachers and see what happens with the teachers. Well, okay, so is it possible to do the same thing with paint all points on a line in such a way that no 2 points exactly 1 unit apart are of the same color? Can we do it with fewer colors than 2?
I don't want to.
No. No. So, if our question to begin with, is, what is the fewest number of colors we need in order to paint all points on the line with that restriction? We solve that problem completely. It is 2, right? The smallest number of colors that we should use on a line in such a way that we avoid having 2 points exactly one unit apart of the same color is 2. Well, there is a name to that. It is called chromatic number of a line, and it has a notation. It's chi. Sometimes people use R1, referring to Euclidean space of dimension 1, or simply chi of 1. We solve that problem right now, and we know that this is 2. This is a great achievement. Well, of course, the next natural step would be to decide what is chi of 2, right? Chromatic number of the plane. We dealt with one-dimensional space, now two-dimensional space. We know for sure, so the question is, what is chi of 2? That's the question. How many of you believe that it is 1? Well, I will ask your neighbors to convince you that you are mistaken this time. So chi of 2 is not 1, chi of 2 is not 2. Is that clear that it is not 2? So is chi of 2 2? Can you give me a quick argument why that is kind of clear that it is not so?
Try an equilateral triangle.
Equilateral triangle. If you start with any equilateral triangle, you have 3 points at, well, length 1, length of the side 1. 2 of these points must be of the same color. At least 2 of these points must be of the same color. Great. We're making quick and nice progress, right? We know now that chi of 2 is definitely bigger than 2. So it's 3 or more, right? Is it 3? Is it 3? Well, there is a nice construction, and that's what Mark actually noticed. We can have this kind of key construction that tells us the story. Equilateral triangle is a nice thing to start with. Let's start with an equilateral triangle, and let us put another equilateral triangle right there. Well, I like that picture. It's very pleasing, very symmetric and pleasing. But I like it so much that I produce another one of these. So I take another one of these. And then I will move these 2 points together. So just imagine that I have these two diamonds, and they are made of some wires or whatever, and I put them at that point. These 2 are the same point. So to begin with, they just hang together. And then I take these 2 points and move them exactly 1 unit apart. On your handout, you have that picture. It has a name. It has Moser's spindle. So with that picture, can you tell me why 3 is not enough? Why having 3 colors won't help us? Can you see that? Everybody sees that? No matter what we do, if we start coloring these 3 points, they have to be with 3 different colors, right? These have to be of 3 different colors. It forces these 2 to be of the same color. If you have difficulty following that, you just do it on your own. Now, it has the name also. That picture tells
You don't
us.
say that during real math circles, do you?
What? No. During real circle, we kids have some. Well, it is a little too much to expect them to come up with this picture.
No, but I mean.
But if you do give them that picture and ask, is it possible to paint these 7 points with 3 colors? You give them, depending on the level of your kids, usually in 5 minutes, someone comes to the board and shows them. And I really do give them this time in the real circle. Yeah.
Well, you have 20 people, so the first one who solves it comes and shows, right? So you have 20 kids solving it, and do I understand it correct that the first one who solves it comes and shows it?
If they want to.
No, if they want to.
Yeah.
What if everybody else is still working on it?
Well, it depends on your circle. It depends on your circle. If usually what I do, I go around and I look over their shoulders and I see how far they are, and quite often they come to the same solution at the same time. If you don't want, if you really don't want, if you feel that people are so engaged and you want to let them continue working on that, you let them continue working on that. It all depends on your situation. Yeah.
So meanwhile, what do you do with the kids that have solved it? Do you?
Oh, that's what happens all the time.
Right.
This is why I prefer, some people don't do that, but I prefer to have lots of problems on my handouts. And in the beginning, I tell students, all kids, I'll tell them that at any moment, if you feel bored with what we're doing all together, just go and solve those problems. If you don't have a handout with lots of nice problems, you can simply put on the board somewhere aside some few difficult problems, and for those kids who are ahead of others. And one of the possible solutions that might be others.
So I've had problems where when I do that, then when I say, okay, so the slower ones have now caught up, and then the quick ones are totally engrossed in what they're doing and don't want to come back.
That's fine. That's fine. Absolutely fine. The whole point is that everybody has fun.
Engrossed in
And and if they have fun doing their problems, fine.
Yeah.
What else to ask? Okay. So that tells us. This has the name that picture has. It's called Moser's spindle because it was invented in 1940s by 2 brothers, and their last name was Moser, and this is why and they invented it specifically to show that pi of 2 is, now we know, it's bigger than 3. It's bigger than 3, so instead of bigger than 3, let me write it is greater than or equal to 4, right? We know that much. Great. Because my time is almost over, I'm going to completely destroy the rest of that circle. But if you look at the handout, you will see that after we discuss the Moser spindle, I actually do that digression into come in, Gloria, come in. So we start. Gloria, there are seats. So we pigeonhole principle. Now this problem, both problems with the circle, with the 2 colors of the circle, it was pigeonhole principle, and this is also pigeonhole principle. It is so simple that we don't really need to invoke pigeonhole principle. But on the other hand, if you do use pigeonhole principle, you can do the same problem, the same demonstration using pigeonhole principle, which is not as fast and not as elegant, but at the same time it allows us to introduce this very deep notion of MN critical configuration. And that MN critical configuration is a real thing that people are really using and invented to try and really find. It's real mathematics. And this is just the beginning. And if you talk about if you come to that point in your circle, you can talk about it and you can say, well now you know what MN critical configuration is. Try to invent an MN critical configuration that will help us to decide what that number is. Okay, and then, as I said, I am completely destroying everything, but I want to, I am eager to find out. I am interested. I really want to know what is that chromatic number for the plane. A very simple construction might explain that it is definitely less than or equal to 9. And suppose that I have tiles, square tiles, and I have infinite supply of those square tiles. And every square tile in my supply has this pattern. It is broken in 9 little squares, and each square is painted different color. So I have colors 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if I have infinite supply of these tiles, it is clear that I can now tile the entire plane with these tiles, right?
How big are they?
How great! You're very advanced. Now, how does it help? Well, if we take the size exactly right, that solves the problem. And what do I mean by exactly right? Well, you have to make sure that within each little square, the biggest distance is less than 1. Oh, by the way, and this is actually, kids in my at least one circle did ask that question. What about the lines in between of these? What do we paint those? And, well, it doesn't matter. You paint them with, this line can be either 1 or 2, doesn't matter. I mean, column 1 or 2, and likewise everywhere. It doesn't really matter at all. So just make sure that the size of your tile is such that this distance is less than 1, but at the same time, when you place the next tile, you put the next tile on, the distance between the closest point of the same color is bigger than 1. That is easy to find. To find this distance is very easy. So, well, great. Now we know that, well, let me do it in a natural order, direction. So chi of 2 is definitely greater than 4, and it is less than or equal to 9. Look, we're making such a great progress. To begin with, there were infinitely many possibilities. Now we're down to very few, right? It can be actually improved, but that was this demonstration is really to do a slightly better thing. Suppose that we have a tile, our mother tile, that is made not of the squares, but of regular hexagons. So I have this mother tile, and in your handout, I believe that the orientation is different. Somehow, when I do it by hand, I always use a different orientation. I don't know why. Okay. So I have this 7 hexagons. This is 7 regular hexagons, and this is my mother tile. And I have infinitely many of those. And you use your colors, and you can use your colors like 1, 2, 3, 4, 5, 6, 7. And it is possible to tile the entire plane using just translations of this mother tile. In fact, it's very easy to do. If you imagine that you have these hexagons, you just continue 3, 4, 5, 6, the colors. And same thing in this row, and the same thing in that row. And you can see that it really does the job. Again, you need to make sure that the biggest distance within your small hexagon is less than 1. And then when you place them together, the distance between the closest point on two different mother tiles of the same color is bigger than 1. And again, that is not hard. It's easy. It's an easy geometric problem, and some older kids really enjoy trying to find the restrictions, what the sizes should be. But well, that tells us something, right? Tells us that pi of 2 is between 4 and 7. Aren't we great? Well, looks like in another couple of hours it's too much probably, another half an hour or so, we would be able to actually find it, right? Well, of course it's wrong. This is the best, that is what is known right now. Nobody knows.
What goes wrong with those 4 squares? A square was broken into 4 colors in 1 square, and then the tiling with the...
Well, what's wrong with 4 colors? Okay, we have 1, 2, 3, and 4, right?
Yeah.
All right. Now we have...
If the diagonal of each one of the
1,
little
2,
squares
3,
is
4.
1.
What?
The diagonal of each of the little ones is 1. The side of each of the little ones is 1 over the square root of 2.
Well, that's a nice question. What's wrong? I know what's wrong. I know what's wrong. The wrong thing is that we know that 7 points is not possible to paint with. Oh, wait. It's 4 colors. No, 4 colors. Okay. Kids, what's wrong with this? Yeah.
The 2 squares that are colored 1, there's a point in one of them and a point in the other one that are 1 apart.
You mean?
It's not exactly that. It's a little bit further. Because you said it's like 1 over the square root of 2 from the boundary of one to the boundary of the other. To go a little bit further up than that, then you'll have 1.
So your inequality is that you have to solve actually over 1. Okay. So as I said, this is what is known up to this moment. People have been working on it for a long time, really. And well, the Moser brothers came up with the spindle in 1940s, and people had already been working on that before they came up with that construction, and they continued working. And up until now, the only thing that is known is that it's somewhere between 4 and 7, but nothing more than that. Moreover, there are people who believe that it is not possible to actually decide that there is something in the axioms of the Euclidean plane that is deficient. That we can tweak axioms of the Euclidean plane so that it actually is anything between 4 and 7. So there are some people who believe in that. So that's a pretty deep mathematics here, right? And you can in 2 hours with good kids, you can pretty much come to that. And they might be really hooked on that problem. There are lots of things lots of smaller and simpler and very interesting and very engaging problems that you can invent to go with that. And I think that once Sam told me that he believes that a good circle should really be run in this way that you do come to open problems at some point. And the kids have this open problem to solve. Nobody has ever solved that problem. How cool can that be if you solve it?